follow some short talks now before lunch. So the first one will be given by Sébastien Kisgan.
Yeah, so I'm Sébastien Kisgan. So I'm Sébastien Kisgan de Richter, and I'm a PhD student at the University of Rennes in France. So in this presentation, in this talk, I report some recent observations and results achieved at the University of Rennes in collaboration with Vladimir Zaitsev of the Russian Academy of Science. In the context of dense granular flow, I lost one slide. So in the context of dense granular flow, an important question is to identify relevant parameters which control the transition between a solid-like behavior to a dense flowing regime. This is the general subject of precursors of avalanches. Experimentally, you can observe that when you incline a granular packing up to the critical angle of stability, the activity of the packing increases. On this movie, you can observe, that's not clear, that the number and the size of rearrangements increase up to the critical angles. So many studies that I have mentioned on these slides refers to parameters which control this critical angle. I think that there's no link.
That's okay.
Yeah.
It's okay.
It's okay? Okay.
Try screwing in the connector. I think it's a connector problem.
A connecting problem?
No.
I don't think that's it.
Try putting it on just display to the projector. Display it to the projector.
Just
If you put it just to display to the projector, it might work.
Tu refais
just
function.
this one. Okay, many studies that I mentioned on this slide refers to parameters which control this critical angle, as the geometry of the system, as the number of layers of the granular packing, or even the influence of walls, if they exist, or the influence of initial packing friction on the dynamics. An original study held by Newen et al. Refers to the existence of large events close to the critical angle, which exhibit intermittency. That's what they call precursors of avalanches. So it remains open questions concerning in particular factors which influence the evolution of these systems. For example, the influence of the initial preparation or the influence of the history of the system on the dynamics. And even influence of the noise as external driving fluctuation on the dynamics of the systems. What's more, no clear link established correlations between events which occur in the volumes and events which occurs at the surface of the packing. Nevertheless, that's a question of great interest to understand internal mechanisms at the origin of its instability. I have problem with slides that are not in good order. So, our experimental setup is constituted on a frame on which we fix a cam and a rectangular box. And all this frame is inclined by means of a threaded stem linked to a stepping motor. And we use two types of measurements to characterize the activity of the packing. We use image processing techniques to characterize the activity at the surface of the packing. So we just measure the number and the size of rearrangements at the surface, and the stored quantity is the proportions of rearranged area compared to the total area of the surface. We also use acoustical measurements. That's a method which has been developed by Vladimir Zaitsev. And between two grains, the static strain is a measure of the intensity of contacts with the relative parameters mu. And the method is to apply the modulated amplitude signal and then by spectrum analysis to determine the activity of the packing rearrangement in the bulk. In fact, you can observe that the fundamental harmonic of the resurged signal is proportional to the square root of mu, contrary to the demodulated harmonic, which is proportional to the inverse of the square root of mu. So following the evolution of the demodulated harmonic is a way to follow the evolution of weak contact networks and to characterize the dynamics in the bulk of the packing. So what are results of optical and acoustical measurements? As you can observe on the first movie, the activity at the surface increases with a tight angle. And here you observe some extreme events close to the critical angles, which are large events and which are related to precursors. So concerning the acoustical signals, we have the same type of behavior with a strong a transition from weak variation to stronger precursors near 22 degrees with large variations to close to the critical angle also. In the following, I also use another variable to characterize the activity of the packing. That's the cumulative sum of the total rearranged area. And you can notice that this evolution is exponential with a transition close to the critical angle which exhibits intermittency related by Newen et al. So an important question I have mentioned in the introduction is the link between optical and acoustical measurements. So we have monitored experiments where we monitored well-in sync optical and acoustical signal. And at the top you have the evolution of the rearranged area. And at the bottom, that's two curves. In black line, the evolution of the demodulated signal. And the red line corresponds to the evolution of the noise component of the signals in the bulk. So we can see that for significant proportions of large events, we can find similar variations in the demodulated signals. That's an indication that the evolution at the surface of the packing is linked with the evolution of weak contact network in the bulk. So moreover, you can observe that there's correlations between the noise and the events at the surface. And it opens the question of the influence of its internal noise, that's a noise created by the system itself, on the dynamics of the systems. A second important point that I have mentioned in the introduction is the influence of preparation of the system on the dynamics. So we performed experiments where we applied series of inclinations constituted of stop and go cycles starting from 0 degrees to here it's 20 degrees. And the left graph represents the activity of the pack during different stages of these inclinations. And each curve corresponds to one stages. And for acoustical measurements, that's the same kind of experiments. And we monitored the evolutions of the signals in the bulk. And each curve corresponds to evolution for each stages. So for the acoustical signals as the optical signals, we can observe a stabilization of the packing. That's evidence of edging in this type of systems submitted to inclination, series of inclinations. And the questions could be, what appears when we exceed this angle theta m? So we perform the same type of experiment. And after 2 cycles, we decide to continue the inclinations towards the angle of avalanches. So the black line corresponds to the total rearranged area for the first passage, and the red line represents the evolution for the ultimate passage. And as mentioned on the previous slide, you have an edging effect in the interval 0 theta m, and exactly at the moment where theta exceeds theta m, the activity of the packing reappears. That's an evidence of a kind of memory effects in the packing. So this preparation of the systems and the history of the system has an influence on the dynamics of this kind of system. We also observe the same kind of behavior for the acoustical signal, with an edging effect in between 0 and theta m, and exactly at the moment where theta exceeds theta m, the activity of the packing reappears. With in gray, you have also the evolution of noise, and you can see that the noise increase exactly at the moment when theta exceeds theta m. So, thanks.
Could you do these things for Gondry's experiment?
What does it mean?
Philippe Gondry showed intermittency or flow. Could you do this measurement on his experiment?
This measurement on this experiment?
Well, both the surface activity and the noise analysis. It would be nice to see whether
Yes,
you were in the transient, what's the difference between the intermittent regime, whether you would see in the rearrangement the intermittence and also in the noise.
Yes, our future work is about the influence of its noise on the dynamics. And to control the noise and to evaluate the influence of its noise on the dynamics.
Question? I have one. Does the acoustic measurement, the acoustic signals, does not change itself the contact network, or is it?
We have a condition that the amplitude of the signals should be less important than the contact, but the static strain, in fact, less important than the static strain.